Okay, folks, we're going to try to lead into a little bit more of the fundamental theorem of calculus here. So we've got some function. We've defined it as the integral from 3 until x. So these x's would be my inputs, and then when I evaluate this, right, if I put a number in for x, I'm going to get a number out. Those would be my output. Those would be my y values. So we want to find a simplified expanded version of f of x by evaluating the definite integral. So in other words, we're going to integrate this. Then once we find f of x, when we have an equation, once we evaluate this thing, then we're going to find the derivative, and some mathemagic is going to happen at that point. So I'm going to encourage you to pause, and I would like you to figure out what f of x is. What's the equation for f of x? In other words, figure out the integral. Okay, let's see how you did. So first of all, these are nice. This is polynomial, so I can just integrate. So that would become t cubed over 3 plus t squared over 2 plus t, defined from 3 until x. Now, because of the first part of the fundamental theorem of calculus, I can now evaluate this by plugging in x and then plugging in 3. So I'll just use parentheses. I don't think I need brackets this time. So I would get x cubed over 3 plus x squared over 2 plus x, subtract, okay, 3 cubed, 27 over 3 is 9. 3 squared is 9 over 2 is 9 halves. 3, which ends up being, I'm going to kill the parentheses right now because there isn't much I can put together. Hey, buoy. So I'm going to go with a decimal. I'm going to be lazy today. So that's what, 4.5, that's 12, that's 16.5. So minus 16.5. Guess that'd be what, 33 over 2? I guess that wouldn't be that bad. Anyway, whatever, I did it. Okay, so this is what f of x is. So this is f of x. So this integral of this function from 0 would be the exact same as this curve that we would get here. Now the second part says, once you find f of x, find f prime of x. And this is where things start to get interesting. So f prime of x equals, what's the derivative of this? So I'd bring the 3 down in front, it would cancel, and I'd subtract 1 from the exponent. I'd bring the 2, it would cancel, I'd subtract 1 from the exponent. I would do the derivative of a, I didn't write my plus in there, it threw me for a second, plus, so this is x cubed over 3 plus x squared over 2 plus x minus 16.5. I do the derivative of x, that's 1. The derivative of the constant ends up being 0. So this is the second part. What do you notice? What happened? Basically, not even basically, exactly what happened is when I derive this, it turns out that the function inside the integral, the integrand, I think it's called, ends up, all the t's become x's, and now I have a function that's really a nice function that we're used to. It's not based on this other variable called t. Now that might not seem all that surprising, but it should be kind of surprising. It should be kind of cool in your head. It should kind of seem like a interesting scenario because we integrate from a to x of f of t dt. Well, I don't know what the integral of f of t is, so let's just call it f of x, big F of x. Minus, remember what we do, we'd integrate this, it becomes some function, and then you'd plug in x, and you'd plug in y. Now, let me do it like this then. I kind of like this better. So I'd integrate this to some new function. I don't know what that new function is, but whatever it is, it's the integral of this function, and it goes from a to x, which means this would become plug in, this should be t, sorry, this should be t, f of t, big F of t. So that becomes f of x minus f of a. But wait a minute, what is f of a? F of a is a constant. So if I try to take this thing and derive it, if I take the derivative of this, it's going to end up, this constant's going to go away, and we're left with just f prime of x. So if I try to take the derivative according to x of a variable based on t with boundaries including x, I can end up with a function that's not based on t at all anymore. So this is the fundamental theorem of calculus as the special case. Basically, it's the idea that I could take my function and replace all the x's with, all the t's with x's. So like if I was trying to integrate this, so d dx of, I don't know what the integral of secant is. If it was secant squared, I would know what it is, but it's secant. I don't know what that is. But let's say it's some function. From 1 to x. Well, that's d dx of f of x minus f of 1. Well, whatever this function is, I don't know what it is, but whatever it is, when I plug 1 into it, I'm going to get some sort of a result. So this is some constant. So now when I derive this thing, I'm going to end up with just f of x, or in other words, secant of x. When I derive this, it's going to turn back into little f, which was secant. All right, so basically, as long as I'm going from a constant to x, I can just basically rewrite the function with x's in there. So let's see how you do with, pause and try to do these next two. Don't overthink them. So I would integrate this. I'd get some crazy integral. Then I'd plug in x into that integral, and I'd plug in 5 into that. I'd integrate this and get some sort of integral. It's some function, right? I'd get some new equation. I'd plug in x into that equation, then I'd plug in 5, and I'd subtract them. Then I'm going to derive that equation. Well, when I derive whatever this is, it's the integral of this. So when I derive it, it's going to come back to this, except I'm going to plug in x. So this would be x cubed under a square root times the sine of x. And then same sort of logic over here. I'd integrate, I'd get some crazy messy equation. I would take all the x's and all the k's in that equation and replace them with x. And I would take all the k's in that equation, subtract all the k's in that equation, replace with pi. But then I'm going to derive that. So when I derive it, it's going to come back to what it was before. All right, so let's just do one. I want to do one bonus question here. Make sure this, point out something I want to point out something here. If big F of x equals the integral from x until 3 of the square root of m squared sine of m dm, then f prime of x equals what? Pause it and give it a try. Okay, well, let's see how you did here. If you look up above, right, all we did was take out the x and replaced it, take out the variable, replaced it with an x. Well, I'd like to do that here with one caveat. What's wrong with this? Notice the fundamental theorem of calculus special case part 2 has the constant at the bottom, our constants at the top, which is going to cause everything to be the opposite. So I need to have a negative, but I can still go through the process of plugging and chugging. Okay, so that's the special case. That's the scenario where we integrate from a constant to just x, because the derivative of a constant is 0. The derivative of x is always 1. This gets a little bit more complicated when it comes to an integral where the boundaries aren't as simple. This is kind of like the reverse chain rule. So if I were to think about this, let's take a look at, let's do it in pink. I want to take the derivative of, okay, so what's the integral of f of t? I don't know. It's some function. We're going to call it capital F. But, okay, we'll just leave it, yeah, f of t. Defined from where? From h of x until g of x. Well, that's the derivative of, so now I'm going to take these values, I'm going to plug them in by the first part of the fundamental theorem of calculus. So I plug this in first, that would be f of g of x. Minus, I plug this in second, this would be f of h of x. Running out of room here. But what are we supposed to do to this? We're supposed to derive this. We're supposed to derive it. So when I derive this function, all of a sudden, got a chain rule, right? You've got f of g of x, which means you need to derive the outside first, then leave the inside multiplied by the derivative. So when I derive this, when I integrate it, I get some function, but then I'm putting a new function in for x. And then when I derive it, I've got a function inside of another function. So when I derive this thing, I've got to do the chain rule. Chain rule. So that would be f prime. So f prime turns it back into little f of g of x times the derivative of the inside. Minus what's the derivative of big F? Little f, h of x times the derivative of the inside. So let's try an example here. So evaluate the following using the fundamental theorem of calculus part 2, and then verify it doing the long way. Well, the shortcut, you'll love it. Well, you might not love it, but it's not too bad. So what you're going to do is you're going to plug in, just like we did before, you're going to plug in this for t, but then don't forget that you have to then multiply by the derivative of that. So this would become secant squared of 2x cubed times, so before we would just stop there. But we now need to times because this function isn't just x, whose derivative is just 1. It's now a chain rule problem, so I have to times by the derivative of 2x cubed, which is 6x squared, and we would get 6x squared secant squared of 2x cubed. So let's do this the long way to show you that this is going to end up being the same thing. So pause. What's the integral of secant squared? And evaluate. Try to don't do the derivative yet. Just try to do the integral. Okay, let's see how you did. So I'm trying to do ddx of the integral. So this is the integral of secant squared is tangent of t from 1 to 2x cubed. Now I'm going to do the first part of the fundamental theorem of calc, where I can plug and chug here. So this would become tangent of, plug that in there first, 2x cubed, minus plug there in tangent of 1. Okay, now we're supposed to derive this thing. Well, the derivative of tangent of 2x cubed, that's a chain. This is inside of tangent. What's the derivative of tangent? Secant squared. So the outside function is tangent something. Derivative of tangent something is secant something. I'm going to use some parentheses here. Times the derivative of the something, which would be 6x squared. Then I'm going to derive tangent of 1. But what's tangent of 1? Some number. It's some number. So when I derive it, it's going to be a constant. So I would get 6x squared secant squared of 2x cubed. Same thing. Same thing. Okay, let's see if you can, right off the bat, something weird's going on here. So I would encourage you to pause for a second and see if you can figure out how to clean this up. All right, so right off the bat, I noticed that this thing was backwards. So my first move is to spin it around. So I'm going to do d dx of the integral, the opposite of the integral from 7 to e to the x of the quantity t squared plus 5t dt. If you want to, you could put that negative in there and go from there. So I'm going to use now the fundamental theorem of calculus general form, shortcut here. So I'm going to be able to integrate. It's going to be a negative, but I'm going to have that negative still. But when I integrate, I'm going to be able to plug this in for t, but then I've got to multiply by that derivative. So I would plug it in first. Multiplied by that derivative, which is e to the x. So what's the derivative of e to the x? E to the x. Now a little bit of a cleanup here. So remember, you can multiply exponents together. So this would be negative e to the 2x plus 5 e to the x times e to the x is, another e to the 2x, right? You can add those exponents together. Wait. I got to distribute that. That's on the outside. Oh, that's got to distribute that negative too. OMG. Now I'm going to distribute. I guess so. Okay. So I distribute this in here. That means I'm going to add another x to this. So it's going to be negative e to the 3x minus 5e. X plus x is 2x. I guess that wasn't too bad. And then let's do it the long way. Okay, so that would mean I'd integrate this. I'm going to leave it as is this time. Let's see what happens when we don't clean it up beforehand. Let's see how messy it gets. Okay, so I'm doing the derivative of. So the integral of t squared plus 5t is t cubed over 3 plus 5t squared over 2. Now I got to put 2 of them around it. From e to the x until 7. Oh boy, that looks awful. Let me try to write it again a little bit bigger. Okay, so this would be d dx of, I'm going to do the integral, which would be t cubed over 3 plus 5t squared over 2 from e to the x until 7. All right, now I want to actually plug these values in there. So I'm going to get down. Hopefully I'm not taking up too much room down here, but we'll see. D dx of, okay, so my first group would be 7 cubed over 3 plus 5 times 7 squared over 2 minus my second group would be e to the x cubed over 3 plus 5e to the x squared over 2. And now I'm supposed to derive this thing, but why do I really like this? Because when I derive this, it's gone. That's just some number. I don't know what it is. I'm going to clean this up before I try to derive this. So this is going to be d dx. I'm going to distribute the negative too. So this is going to be negative. When you have e to the x to the 3, we can multiply it. So e to the 3x over 3 minus, same thing here, 5e to the 2x over 2. All right, let's try to derive this thing. So what's the derivative of negative? Negative. What's the derivative of e to the 3x? E to the 3x over 3 times, this is an out, that's a constant, right? That's negative 1/3. That's out front. So my function is e to the 3x. That's a chain. E to the something is e to the something times the derivative of that something, 3, minus, I've got my coefficient of 5/2 again, times, what's the derivative of e to the 2x? Well, that's another chain. E to the 2x times what's the derivative of 2x is 2. So my 3's are going to cancel. My 2's are going to cancel. I'm going to have negative e to the 3x minus 5 e to the 2x. Same thing. All right, so now we never have to do it both ways again, I hope. Maybe in the homework you have to, but I don't have to. All right, so let's do example 11, and then we'll call it in this section before we get into the mean value theorem. All right, try to set it up first. Let's see what it looks like. See if you can get this first part going. Okay, let's see how you did. Okay, so f prime is equal to the derivative of this. So when I derive this, remember we can plug in, but then we've got to multiply by the derivative of that thing. So I'm going to have natural log of 3 to the x, times, now you got to go way back and remember how to derive 3 to the x. It's probably been a long time. I'm going to go up to the top here and write a little note, a little reminder. d dx of, let's go b, we'll just call it base to the x is equal to, so as always, it always starts off the same. Base to the x, but then you have to do a natural log of that base, natural log of b. So using that as a clue, see if you can finish the rest of that first part. So you should have gotten, so I've got the natural, this good plugged in, then I got to derive 3 to the x. Well, 3 to the x is going to become 3 to the x times natural log of 3 minus, now I'm going to take this nastiness and plug that in first, natural log of 2 plus sine of 2x times, okay, so my outside function is natural log, my inside is this. So to do the derivative of this, I've got a problem. Well, first of all, what type of rule is it? So it's a sum rule. So I'm going to derive this. Life is good. That's gone. Now I need to derive this. What type of rule is it? It's a chain. I've got sine of something. So the derivative of sine of something is cosine of something. I wish I would have done a better job of colors here, but that's life. Times the derivative of the something. The derivative of 2x is 2. Okay, so let's see if we can clean this all up. What would be the nicest way to write this? There is no nice way here. I'm just going to smash this all together. Natural log of 3 to the x. I suppose, yeah, I'm not going to worry about it. Times, let's at least push the 2 out in front. Not our prettiest answer of all time. But this is a free response question, so why bother cleaning it up? You could have just left it as that if there's free response. Don't clean it up at all.